So state of matter is very simple. It's something you can finish in 1 hour. We are doing at least we are finishing that topic and entering another topic today. It's not much. So let's look at it. It's very simple and straightforward. Though, don't please remind me. I need to solve question and send it to you. Remind me that as I want to solve question on state of matter, particularly and chemical bonding. Step question to you. They are simple things. Now, state of matter, please. Can you read? How do you know? Let's read the syllabus first.
Explains the origin of pressure in a gas in terms of collisions between gas molecules and the wall of the container.
Thank you. Yeah, look at this. Before you start, I put some introduction here. Can you read, please?
There are states of matter. There are two factors which determine the state in which any matter exists. One, strength of forces between its particles.
It's okay. It's okay. If the forces are strong, will it be a solid or a gas? If the forces are very strong, will it be a solid or a gas? I'm asking you.
Solid.
Calm down. Forces between the particles. Thank you. To be solid. What if the forces are very, very weak? What will it likely be? Thank you. So if the forces, look at it now. For example, SiO2 is a solid. Water is a liquid. CH4 is a gas. What does this imply? You are telling me that the forces that hold. Look at now. Pay attention. I'm showing something now, please. Now, these forces, we call it IDID. Is allowing it. IDID forces. What does IDID forces mean? Instantaneous dipoles, induced dipoles. Is it going to do it under this topic again? They are the weakest type of intermolecular forces. For water, we have hydrogen bonding. For SiO2, what kind of bond hold it together? Have you did you write IGCSE or which exam did you write? O level.
IGCSE.
Do you remember macromolecular structures?
Yes, I do.
Give an example or giant covalent structure.
Macromolecular, graphite, diamond.
Diamond, graphite, and what? Silicon dioxide. Do you remember those three?
Silicon dioxide, yeah.
Let me tell you what that means. Please pay attention. You are saying that in silicon dioxide, silicon and oxygen covalent bond. Please look up. I want to circle something now. Look at what I'm circling. I want to circle something. Please pay attention. This is silicon dioxide. This is also silicon dioxide. This is silicon dioxide. Can you see now? This is silicon dioxide. Now, what hold them together again? Covalent bond again. Covalent bond within silicon dioxide. Covalent bond in between silicon dioxide. Do you get the point now? So we call them giant molecular structure or macromolecular structure. Water molecule, what hold which kind of bond hold H and O together in water molecule? H and O. Which kind of bond hold them together? H and O. Which kind of bond hold them together?
Covalent. Yeah.
Thank you. But between water and underwater molecule, what hold them together?
A hydrogen bond.
Thank you. Now in CH4, which kind of bond hold C and H together?
In CH4?
Yes, methane, look at it. CH4, Cl2. CH4, Cl2, all of them. What kind of bond hold the two atoms together? What kind of bond hold them together? The two atoms in Cl2.
In Cl, that's a covalent bond.
What did you say?
Covalent bond.
Thank you. But between Cl2 and Cl, what hold them together? IDID forces.
Yeah.
So that means it is not the covalent bond in Cl2 that determines the melting point of Cl2. When Cl2 undergo a change of state, you are converting Cl2 solid to Cl2 liquid to Cl. You didn't break the covalent bond between them. Do you get the point now? So the forces are very weak. So number one, what determines the state of matter? The strength of bond between the molecules. If the bonds are very strong, it will be a solid. If it's very weak, it will be a gas. If it's intermediate, it will be a liquid. Is that okay? Settled. So now look at this. I wrote for SiO2, strong covalent bond. I wrote it so that you can correlate the color. Look at the color. Correlate it. SiO2 is in blue. Strong covalent bond. SiO2, strong covalent bond. The NaCl, strong ionic bond. Do you agree? So they are strong. But in water, what hold them together? Hydrogen bonding, which is relatively weaker compared to ionic bond or covalent bond. In CH4 and in Cl2, what hold them together? Weak IDID4. They are the weakest of all of them. Therefore, if they ask you, why is Cl2 a gas and water a liquid, what would be your answer? 2 marks. Why is Cl2 or CH4? Why is it a gas? whereas water is a liquid. 2 marks. What will
CO2 is a gas because it has very weak
ID force between its molecules.
ID forces as compared
Whereas water is a liquid because it has relatively stronger hydrogen bonding. We are comparing that. So you can just say, you can say Cl2 has ID forces between its molecules. Water has hydrogen bonding. That's 1 mark. You now say hydrogen bonding is relatively stronger than ID forces. No, so do you get the point now?
Yeah.
Tell me what they have and tell me which one is stronger. 2 things you have. Anytime you take, you compare a state of matter. Tell me what forces are holding the molecules together. Then tell me which one is stronger. Okay, again, why is water a liquid and NaCl is a solid? What will you tell me?
Why is water a solid?
Water has hydrogen bonding between its molecule. NaCl has ionic bonding between its ions. Ionic bonding is stronger than hydrogen bonding. Can you see the answer? Tell me what they have and tell me which one is stronger. Should I repeat that again?
Yes, please.
Water molecule has hydrogen bonding between its molecules. NaCl has ionic bonding. That's 1 mark. Now tell them that ionic bonds are stronger than what? Hydrogen bond. No story. That means it takes more energy to break ionic bond than hydrogen bonding. Do you get the point now?
Yes.
So if they tell you why is water having lower boiling point than NaCl, the same answer. Water has hydrogen bonding between its molecule. NaCl has ionic bonding between its ions. Don't use molecule for NaCl. NaCl they are made up of ions. NaCl has ionic bonding. So in NaCl, I need to open a blank page where I can do jotting sometimes. Now, where is my blank page here? So in NaCl, look at NaCl. Between Na plus, no. State of matter. These are, there's no way I will not put some little class notes again. I'll send both of them to you so I can go over it. Now look at NaCl, Na plus and Cl minus. What hold them together? Ionic. Within this is ionic. Am I right?
Yes.
Now look at that one. Na plus and Cl is also what? Ionic. Now look at what I'm drawing. I want to draw that now. Look at this now. Now this one again is still what? Ionic. So ionic within, ionic across. Everything is ionic. So that's going to be very, very high. Do you get the point now? But, so if I'm to say now, so I will write some things on the board and look at it. I'll write SiO2 is a solid, CO2 is a gas, water is a gas, NaCl is a solid. I'll do one more. Okay, hold on. Cl2 is a gas. Yeah. Bonding, structure, forces between particles, forces, strongest forces, let me put it that way. Strongest force between the particles, the strongest of them all. Strongest forces between what? Between particles. So yeah, let's go. Copper. Yeah, let's go. You are telling me the bonding in each of them. You are bonding in those guys. Yeah, bonding. This guy is, of course, covalent because remember this covalent, covalent,
ionic,
covalent, then copper, metallic.
Metallic.
Do you agree?
Yes.
Now let's go. Structure. This guy is giant covalent. Is giant. This guy is simple covalent. Simple. It's also simple covalent. This is also giant ionic. This is simple covalent. This is giant metallic. So there are 3 types of giants. It can be ionic, it can be covalent, it can be metallic. Are you listening to me?
Yes.
Good. Giants can either be covalent, e.g. SiO2. Can be ionic, that's all ionic compound. And can be metallic, all metals. Is that okay? Now let's go. What is the strongest force between the particles of SiO2? It's covalent. Between SiO2 and SiO2 is still covalent. This guy, This guy is what? ID forces. Aha. Do you get the point now?
Yeah.
What about water? Hydrogen bonding. What about this guy? He's still ionic. This guy, ID forces. And finally, copper and core is still metallic. Can you see now? Look at the giant one. Look at the giant one. Look at it. So I can get them. Covalent bond within, covalent bond across. Ionic bond within, ionic bond across. Metallic bond within, metallic. Can you see now? They don't change. Covalent within, covalent without. Covalent bonds are stronger, sometimes stronger than ionic bonding. Why? Diamond is one of the hardest material on earth, and that's covalent bond. Do you get it now? So,
Yes.
covalent, you have covalent within, covalent across, ionic within, ionic across, metallic within, metallic across. Which of them is higher? Any of them can be higher. Now, I'll give you examples so I can understand. Look at it. Cobalt is a metal. Cobalt is a metal. It's a metal. Melting point is around 2820 degrees Celsius. Can you see? No, 2800. No, 22. It's about 2800. 2800 degrees Celsius. Now, look at aluminium. It's a metal. Melting point is around 650 degrees Celsius. Now, that's one. Now, look at SiO2, giant covalent. Melting point is around 1620 degrees Celsius. Nobody has all of these. Don't worry. I'm just giving you, like, I'm trying to drive home a point. Let you know that any of them can be higher. Is that okay? 1620. NaCl. Melting point is 801 degrees Celsius. MgO. Melting point is around 2820 degrees Celsius. Now, diamond. Melting point is around what? 3700 degrees Celsius. Now, pay attention.
Mm-hmm.
Is there a metal that has higher melting point than an ionic compound? Can a metal have higher melting point than an ionic compound? From what I've written here. Can a metal have higher melting? Yes, look, I'll show you one. Look at this metal. Look at this ionic compound. Metal is higher. Do you agree?
Mm-hmm.
Can metal also has higher melting point than giant covalent? Yes, that's correct. Look at this metal. Look at this guy. So metal can be higher than ionic. Can be higher than covalent. Do you get the point now? And now
Yes.
let's turn it around. Can ionic be higher than metal? Yes, of course. Look at this ionic. Look at this ionic. Ionic higher than this metal. Am I right?
Yes.
Can ionic be higher than covalent? Yes. Ionic, covalent. Now let's turn it again. Can giant covalent be higher than metallic? Yes. Giant covalent and what? Metallic is higher. Can giant covalent also be higher than ionic? Yes. Giant covalent, ionic. So my point is this: you cannot say one is higher than the other. All of them are high. Anyone can be higher than the other. Do you get it? Just know that there's a giant metallic which can be higher than covalent and ionic. There's a giant covalent which can be higher than metallic and what? Ionic. There's not a giant metallic which can be higher than both of them. Any of them can be higher. Is that okay? But if they ask, they say, if tell you that, listen, they said aluminium melts at 650 degrees Celsius, whereas SiO2 melts at what? 1620 degrees. What's the answer? What will be your reason? Give reason for the what will be your answer? Just say that, oh, the covalent bond in SiO2 is stronger than the metallic bond in Al. That's your answer. So it takes money to do it. Anyone that desire is stronger. Just say covalent. Oh, I don't like that color. Just say covalent bonds in what? In SiO2 are what? Stronger than what? Metallic bonds in Al. That'll be your answer. Anyone can be higher than anyone. So let me now do another for you. What if I give you cobalt and sodium chloride? 801 degrees Celsius. 801 degrees Celsius. What's going on now? 1 minute, please. 81 degrees Celsius. This guy is around 2800 degrees Celsius. What will we answer here for this melting point? Just say all they want to hear from me is metallic bonds in what? In cobalt are stronger than what? Complete it now. Stronger than. Hello.
Than the ionic.
Thank you. Than ionic bonds in NEC. That's all they want to hear from you. Ionic bonds.
Yes,
So
sir.
anyone can be higher than anyone. Let's now do metallic. Let's do SiO2 melting point 1620
Mm-hmm.
and NaCl again melting point 801 degrees. What we tell them here?
Covalent bond is
Bonds
stronger
in
than the.
SiO2 are stronger than what? Ionic bond. You don't want to hear the word covalent ionic, and you not tell that, oh, therefore more energy is required to break the ionic covalent bond in SiO2. Do you get the point now? So for
Yeah.
the giant guy, anyone can be higher than anyone. They are all giant. Don't get me wrong. They are all giant. But it depends. Anyone can be higher than anyone. But now let's go for giant covalent again. Look at this guy: carbon, silicon, germanium. They are in the same group. They all have giant covalent structure. Giant covalent what? All of them structures. Are you following me, please?
Yes,
Which
sir.
of them do you think? Which of them do you think be higher melting point? Pay attention. Look at carbon. Carbon is like. Look at carbon. Carbon is this. The atomic radius is very small. Do you get? So can you see how carbon is? This is carbon. This is carbon. Silicon is this. Is bigger, longer. Are you there?
Yes, sir.
Longer, longer, longer. This is silicon. Longer, longer, longer. Now, which of them? So if the carbon is silicon, which one has a stronger covalent bond? Carbon is. Look at carbon. Look at carbon. Atoms are very small in size. Covalent length. Silicon bigger in size. Can you see now? So which covalent bond will be stronger? Carbon or silicon? This is carbon. This is silicon.
Carbon.
Thank you. The smaller the radius, the shorter the bond, and the stronger it is. We said that. Is that okay? So here we have shorter bond length, higher bond energy. Am I right? Therefore, higher melting point. Higher melting. Do you get the point now? So when you compare covalent, that's how you compare them. Giant covalent. The one that have smaller size, the bond will be very strong. Why? The electron shared. Look at it. Nucleus and nucleus. Nucleus is here. Nucleus. Electron shared are very close to the nucleus. So the attraction is very, very strong. The other guy, look at it. Silicon. Nucleus is here. Nucleus is electrons are here. So electrons are a bit far from the nuclei. Therefore, the bond strength will not be as strong as the shorter one. Do you understand what I'm saying now? The shorter the bond, stronger it is settled. When you now have it, so that's a group of covalent compound that you can want to compare, a group of that are comparable. You cannot be comparing diamond and, or you cannot be comparing whatever and whatever. Now, in fact, if you look at this again, look at this. Boron is also giant covalent. Boron is giant covalent. Giant what? Covalent. So is carbon. Carbon is also giant covalent. Which of them will have high melting point and why? Again, radius, atomic radius decrease across period. Do you remember that? Good, thank you. So look at boron. So anything they give, you can always interpret it. Boron, nucleus, electron, electron. Carbon is smaller in bit. Carbon, nucleus, it's two electrons. Can you see now? So radius this way. Atomic radius decrease across atomic radius. Decrease is too sharp. Let me increase it a little bit. Atomic radius decreases across what? Periods. Therefore, bond length increases. Bond length will what? With decreases across period. Therefore, bond energy will bond energy increases. Is that okay? So we expect covalent bond in carbon to be stronger than covalent bond in what? In boron. Again, we expect covalent bond in carbon stronger than that of what? Silicon, because silicon radius is increasing down the group. Carbon and silicon are in the same group. So as they're going down the group, the atom is becoming bigger and bigger. The bond length is becoming longer and longer. The bond energy is becoming lower and lower. Do you understand it, Tamuda?
Yes, sir.
Now with giant covalent. Now let me deal with giant ionic for you. I'm summarizing this topic for you. I've not started it. I'm summarizing this summary will help you understand. We'll just roll over it to know now. You understand it? Now, giant ionic, if I have a group of giant ionic guys, how do I know the one that is higher? How do I know the one that is higher? Giant ionic. Let me double this. I can do giant covalent here. This one. First of all, what I taught you today is that I say all those giant guys, anyone can be higher. All of them are all high. Sometimes covalent is higher, sometimes ionic is higher, sometimes metallic is higher. They give you to compare them. Of course, you know what to write now. Am I right? Giant covalent structures. I'm done with it. Now, let's go for giant ionic. Pay attention, please. Now, let's take element in the same group. Yeah, let's go. I mean, the same period. Lithium. Okay, yeah. Lithium chloride. Sodium chloride. Are you there? Potassium chloride. They all have a giant ionic. But lithium is smaller. Look at lithium. Very small in size. Chloride. Sodium is bigger in size. Chloride. Potassium is very big in size. Chloride. Which of them do you think we have stronger attraction between them? The smaller guy or the bigger guy?
The smaller guy.
Thank you.
Lithium.
So as we are going this way, I'll tell you what to write. And any covalent compound, whether they are all oxide or they are all whatever, all of them, the answer is number one. Simple. Just say that ionic radius increases. Daniel. For that is I feel like maybe I'm going to do this one. You go on love school now. You might want to lie. To Andy, no tenants could be something else. My girlfriend. Watch of whom could be something go no somewhere. Be there, no school now. Why are you troubling yourself? But watch of good, mom. I'm sorry for distraction. Sorry for that. Ionic radius increases, then charge density decreases. Can you try to explain to what you mean by charge density?
Charge density.
What's not population density? Number of people per unit area. What's not charge density? Charge per unit area. Now look at this old guy is +1. This bigger one is still +1. This very big guy is still +1. Which of them do you think has greater concentration of charge per unit area? The smaller guy.
Yeah.
You get that? The charge is got this small guy have +1. This very big guy also has +1. Smaller guy, the charge that means that +1 is concentrated in the small space. Charge density, charge per unit area. Is that okay? Do you get the point? So charge density decreases, therefore, electrostatic attraction between ions decreases. So melting point decrease. Tamuda, does it make sense to you?
So you're saying for charge density, if it's in a smaller area, the density is high.
Just like when 10 million people are living in a small town, is that not high population density?
Yeah. Oh, okay.
Right. Maybe you have 2 towns in your area now. One town, like Lagos in Nigeria now. Or let's say, okay, which country? I think what's the most populous country in the world? They mention one country like that. It says the one that have the greatest population in the whole world. They mention one town like that. Is it Tokyo? I can't remember. They mention one city like that. It's in the whole world. When they compare the size, it's not that the population is greater than any other person. No. When you consider the area and the people living there, like now, look at it. 1 square meter, 2 square meter, 1.5 million people, 2 million people. Which one has greater population density?
1.5.
Thank you, because that is 1.5 in one. This one is like 1 million in what? In 1 square meter. That's it now. So the charge out so what the term charge density is this? Look at it. Charge density is proportional to charge inversely to radius. or size. Do you get the point now?
Yes.
If the charge is high, charge density is high. If radius is small, charge density is high. Based on that, tell me this. Look at this: sodium chloride, sodium fluoride, magnesium oxide. Oh my God, the difference is too much. This guy is around maybe around maybe 1,000. This one is around 2020. You know why? It's very simple. Please pay attention. Sodium is bigger than magnesium in size. So this is sodium. This is smaller in size. Magnesium is smaller. It also has +2. Wow. Fluoride is bigger. Fluoride is what? Fluoride is this. Oxygen is this. Look at it here. So +2 and -2, they will attract themselves more than +1 and -1. Do you agree? The melting point of H2O is too higher than that of NaF. So when you have smaller size and higher charge, you have greater charge density. Is that okay?
Yeah.
When you have smaller size and higher charge, you have greater. So this guy is much less than this, much more less than this. Is that okay? So now this three, which of them will be higher? Which of them will have the highest melting point? Sodium chloride, sodium oxide. No. And this guy, Na3N. Look at this three guy. Which of them will have the highest melting point? This guy is between what? Na plus and Cl minus. -1 plus. What is between what? Na plus and O2 minus. This guy can call Na plus and N3 minus. Which one will attract more? N3 minus. Do you agree? So this way.
Yes.
Melting point should increase. Am I right?
Yes.
I'm sure you get the concept now.
I do.
So if it is down the group, the charges will not change. You capitalize on radius. That as radius is increasing, there's a decrease in charge density. The attraction dwindle down the group. They become less melting point. But if it's across the period, you capitalize on charge. Magnesium compound, they always have, most often than not, they have higher melting point than sodium compound. Do you get the point now? For example, now, sodium fluoride, magnesium fluoride, aluminum fluoride. This guy is in Al3 plus, we attract the iron more. Mg2 plus, we attract it more than Na plus, but not as much as Al3 plus. Na plus, we attract it the least. Do you agree? Again, this way, melting point increases. Melting point. What will be your reason? Ionic charge of the cation increases. And we just say ionic charge of cation increases and ionic radius decreases. What does that mean overall? That means charge density is increasing. Charge density increases. Am I right?
Yes.
Therefore, what does that mean? Attraction, the electrostatic attraction between the ions, electrostatic attraction between ions increases. So melting point increases, melting point increase. So I've given an example of what? Giant covalent, so when they go with many, the one that they will likely be higher. Why is diamond higher than graphite in terms of melting point? Diamond has strong covalent bonds only. Graphite is a mixture of covalent bond and weak van der Waals forces. Though they are both giant molecular structure, but diamond has covalent bond only throughout this molecule. Diamond is a mixture, graphite is a mixture of covalent and what? Weak ID forces. Is that okay? Therefore, we expect diamond to have higher melting point than graphite. They are both high, don't get me wrong. Diamond is about 3,700, graphite is about 3,500. They are both high. But why is diamond higher? Covalent bonds only in diamond. What about graphite? A mixture of covalent bond and what? And van der Waals forces. Is that okay?
Yes.
Get it? Then again, we've done that of ionic. Let's now go for metallic now. Metallic. That comes out in chemistry very well. They said, tell us reason why the melting point of group 2 metals are decreasing down the group. Calcium, rubidium, no. Calcium, strontium, and barium. Calcium, strontium, and barium. Now, for you to understand, you need to know what the metallic bonding is. Metallic bonding is like this. Look at it. Let's say beryllium. Beryllium is actually like this.
A lot, and you're like, okay, do you have a private tuition? Don't you have? Do you have? And yes, Ajiro Tech do have a private tuition. So by my right, you can see that we have for the Edexcel and Cambridge IGCSE, and yes, we do have for all subjects. Okay, all subjects. Okay, the popular ones that's always been in demand is mathematics, English language as a second language. Okay, we have physics, we have biology, we have chemistry, and we have the flagship, which is ICT, just here and there. We also have business studies. So if you're interested for a private tuition, I think all you have to do is send an email to the sales team at ajirotech@gmail.com, and they would reply to you, talk about your time zone, talk about, and the fee is really quite affordable. It's really quite affordable. It's when you look at it across other tutoring service, I think this is the one that's quite affordable, and you get the very best of service. We also have for the E-levels as well, and also for the Edexcel. So we have for the Cambridge E-levels and Edexcel E-levels. Okay, and we have also across the subject mathematics, which is usually the hot cake when it comes to E-level, mathematics and chemistry, and then biology. These are usually one of the ones we have in demand always, all the time, even physics, for E-level. So all you have to do, if you're watching this right now and you are interested for a private tuition, then you can do yourself a solid, okay, and send an email to the sales team at ajiro@gmail.com, and they'll reply to you. And the good news about this is, what I've discussed with the sales team is, we've tried as much as possible to see how we can subsidize the amount according to countries, so it doesn't really look very, very heavy. Okay, so so this is really important. Yes, we do charge in pounds, but again, we try to be as much as possible considerate to your countries, and we don't just skyrocket the price. No, because at the end of the day, we know how it feels, and we really want you to actually get the best of service, and again, be able to afford it from the comfort of your home. So again, Ajiro Tech private tuition is currently ongoing. You can enroll yourself for the IGCSE, and then for the E-levels. Again, for the IGCSEs, these are the subjects, and for the E-levels, these are also the subjects. So again, what are you waiting for? Just send an email to the sales team. If you're an IGCSE student preparing for IGCSE, if you're watching this in 2025, when this is in 2026, when this is 2027, we're currently ongoing, and this is actually a good time for you to actually explore, and then get it tailored to your own needs. So trust me, you don't want to miss out.
If I want to be more precise, let me not judge general one. Yeah, okay, it's all right. It's okay. That's fine. Beryllium. Beryllium metal is like this. The way about calcium is like this. Maybe barium is like this. Can you see?
Yes.
Now, what are the particles present in the metallic bonding? Did I put it? Did I write? Oh, let me write giant metallic. I'm done with this guy. Giant metallic. What are the particles present? We've said it before. You should be able to know it all.
Ions, atoms.
No, ions, not atoms. They are charged. Cations in a sea of delocalized electron. Do you agree?
Yes.
So we have ions and delocalized electron. Do you remember that?
Yes.
Now look at the ions here, they are bigger in size. So the attraction between the ions and the localized electron is becoming weaker and weaker as we are going down, because the atom is becoming bigger in size. Therefore, the charge density of the ion is decreasing. Do you agree?
Yes.
Their charge density is decreasing. They're becoming bigger and bigger. The radius, the what now? The cation, the charges do not change. They are all plus 2, plus 2, plus 2. Do you agree?
Mhm.
So as we are going this way, so for metals, for any metal down the group, number 1, atomic radius of metal increases. Am I right?
Yes.
Or you can say ionic radius of the cation, if you like. Since that is what is there, is that okay?
Mhm.
Ionic radius of metallic ion increases. Ionic metal of metallic what? Metallic ions increases. The charge does, the charge is constant. Do you agree? They are all plus 2, plus 2, plus 2 throughout. So because of that increase in radius, charge density decreases. Do you agree? Charge
Yes.
density decreases. Tell me what does that mean? Metallic bond strength decreases. Metallic bond strength. Or if you like, electrostatic attraction between cations and electrons decreases. Therefore, does that mean melting point decreases? Melting point decrease. So across down the group, we expect a decrease in melting point for metal. Any metal you group, is that okay? Do you
Yes.
agree? But if they
I
are same period and similar, as in sodium, magnesium, aluminium. Sodium is this. Now, in this case, I would like to be precise now. I won't draw a general one for you. Sodium is this. Na plus, Na plus, Na plus, what about magnesium? Mg2 plus, Mg2 plus, and it's smaller in size, so Mg2 plus, and Al3 plus is smaller still. Al3 plus, Al3 plus, Al3 plus. Let me do any bigger. Na is bigger than all other one because we just decrease across the period. So look at it. Na, this better. Na plus, Na plus, Na plus. Now show the electron in between them. Yeah, what are the electron now? The localized electron. But there are 4 cations, so 4 electrons. How many electrons will be 8? 8 electrons, but there are 4 cations. Each of them will lose 2 electrons, right? 1, 2, 3, 4, 5, 6, 7, 8. Here there should be 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you know, if they ask you why is there an increase in electrical conductivity, number of localized electron increases, so they conduct better. Do you agree? That's no story.
Could you please repeat that, sir?
Why is there an increase in electrical conductivity? Electrical conductivity. Because as we are going from sodium to aluminium, number of localized electron is increasing, or you say electron density is increasing. Do you agree? They're having more electron in
Yes.
their shell. Therefore, they should become better electrical conductors. Is that correct?
Yes.
Now that's electrical conductivity. It should increase because of increase in what? In the number of the localized electron. Do you agree?
Yes.
What about the melting point? The attraction between Na plus and electron, Mg2 plus and electron, Al3 plus, Al3 we attract more. Am I right? So you can say this way again. Ionic radius of metallic ion decreases and charge magnitude increases. You agree? So what does that mean? Implies charge density increases. Charge density increases. What does that mean? Would they become stronger metallic bond or weaker metallic bond?
Stronger.
Thank you. So metallic bond becomes stronger. Metallic bonds become stronger. So what will happen? Melting point increases. I'm just this makes sense. So that's generally that's what you are learning today. Giant metallic, giant covalent, giant ionic. That's gone. Then simple molecular. That's 14 you are learning. All substances belong to one of them. Either it is giant ionic, giant covalent. Then now, I wanted to draw something for you. Okay, yeah, don't worry. Okay, that's fine. Now let's go back to our work. So number one, we have seen this now. So he said we should now the first thing he said your slabo was that tell them the origin of pressure. Am I right? Look at it. Origin of pressure. Am I right? Look at it.
Yes.
Let me explain that to you. Look at that diagram. Yeah, look at it. A, B, C, D. How many molecules are in A? I think it's seven molecules.
Yeah.
Let's just say 7 molecules in A, 7 in C. So A and C, and 7 in D. 7 in D. Now, A, C, and D, which one has the greatest pressure?
C.
Thank you, because it has smaller volume. So pressure and volume are inversely proportional, other factors being equal. Do you understand what I'm saying now?
Yeah.
Pressure and volume are inversely. That we call it Charles law. Not in IGCSE, not in A-level, in WAEC. Pressure and volume are inversely proportional. Other factors being equal. That when you decrease volume, pressure should increase. Why? Who can tell us why? Can you tell me why? Why an increase in volume, a decrease in volume will lead to an increase in pressure? Because when you decrease volume, actually, pay attention to this. Pressure is actually arises due to collision on the walls of container. Pressure arises due to what? Due to collision. Oh, it's there. Look at it. Can you read this?
Pressure is a result of collision between gas molecules and the walls of the containing vessel.
So the more they collide the walls, the greater the pressure. Is that okay?
Yeah.
So if they are now confined into a small space, that means they will collide with the walls more frequently. Do you agree to that? And generate more pressure. So ACD, C is the highest pressure, followed by A, followed by D. Is that okay? Now compare A and B. They have the same volume. Which one has greater pressure now?
I'd say B because there are more
That's more molecules. No story. No, that's more molecules. The more the molecules, if you keep the number of now, I will show you that. Look, we have said number one, we said P and V are inversely proportional. Am I right?
Yeah.
That's one. Then again, you know that P and T, they're really proportional if volume is constant. In this case, T equals to what? Constant. In this case, V equals to what? Constant. If I now connect all the three together, I can now say, I will do that later. PV equals nRT. N is the number of mole. So the greater the number of mole, the greater the pressure. Do you agree? Am I right? From here now, you can see that pressure and number of moles. So we can say pressure and number of mole, where N equals to what? Moles. They are directly proportional. Is that okay? Yes. If you add more molecules, of course, the greater the pressure, other factors being equal. That's how we can explain A and B. In A and B, there are more molecules in B. So the molecules are more crowded together. The intermolecular distance between the molecules decreases. So they collide more frequently with the wall of container. So they generate what? More pressure. Is that okay? So I gave you, I said P is greater than B. B contains greater number of molecules. Frequency of collision is greater. C and A. I said C greater than A. C contains smaller volume, therefore reduce intermolecular distance, therefore greater frequency of collision on the walls of the container. On the walls of container. Is that okay?
Yes.
So what can you do to increase pressure? Yeah. Number one, increase the mole of particles. Is that okay? Increase the temperature while keeping volume constant. Decrease the volume while keeping temperature constant. That's what I told you here. Look at it. When you increase for this one, here, decrease volume, keep temperature constant, pressure will increase. Increase temperature, keep volume constant. Increase the mole of gas, keep every other factor constant. Do you get the point now? So
Yeah.
for three factors affect pressure now. The volume, lower volume, greater pressure. temperature, higher temperature, higher pressure. The mole of gas, the more the mole of gas present, the more they collide on the wall of container, the greater their what? Their pressure. Am I communicating here?
Yes.
Thank you so much. So that's all the story. I'm sending it to you. So now let's go. Next thing after that. Number two. Can you do number two?
Understand that ideal gases have zero particle volume and no intermolecular forces of
Number
attraction.
three. Number three.
State and use the ideal gas equation PV is equal to nRT in calculations, including
Thank you.
the
Now
depth.
this number two. He's talking about ideal gas. What's an ideal gas? An ideal gas is a perfect gas. It does not exist. Pay attention.
Mm.
Now you have to pay attention now. Ideal
Yes.
gas is an imagination in your mind. It does not exist. Now let me give an example. Ideal student does not exist. Ideal student is the one that gets 100% in all his exams. He does not come late to school at any time. When the teacher teach him anything, he understands everything 100%.
Mm.
He does not get that. He gets 100% all his course. He submits his assignment to time. He does not come late to school. He still, are you an ideal student or not?
Sir?
From what I've said, are you an ideal student or not?
No.
So can you now say ideal student does not exist? Ideal
Yes.
teacher does not exist.
Mm.
Ideal gas does not. It's an imagination in your mind. It's a perfect gas. It doesn't exist. But some are closer to ideal than others. Do you get the point now?
Yes, sir.
If you always come to school on time, me and you were students in the school, you always come to school 7:30 every day. Me, I come to school after 8. After 8. Sometimes assignment, I will not submit. I will go and beg my teacher, sir, sorry, I didn't submit my assignment yesterday. Can I submit this today? You submitted your own at the time. Though you are not ideal, but you are closer to being an ideal student than me. Do you get the point now?
Yes, sir.
So some students are still, some gases are very close to ideal. Some are very far from it. But there is no perfectly ideal gas. That's my point. There is no perfect, it doesn't exist. It's like saying perfect beauty. There's no perfect beauty on earth. Somebody say the beautiful ones are yet to be born. Am I right?
Yes, sir.
When you say you find as a girl, I tell you say that girl, say you find past you. The one that the Miss World is a lie. That will say he won't Miss World. It's not the finest in the world. There are girls who
Yes.
are finer than her. They don't have the place. Some of them are living in the village. They are very fine. They don't use makeup. They don't use cosmetics. They don't use anything. And they are naturally beautiful. Do you get the point now? They don't attach
Yes.
me. They don't paint it. And they are. So I'm saying that when you say perfect beauty, it does not exist. Perfect husband does not exist. So when you want to marry tomorrow, stop looking for a perfect man. You won't see one. It does not exist. I want a very caring man, a very religious minded man. That one that is religious, those that don't do bad things. The one that will be caring for me, and I've got very wealthy man, and very handsome a man. If a man they handsome and is very wealthy, guess we clog around him. She will not likely be faithful. He will not likely be faithful, most likely. He's very
Yes.
handsome and he has money. Most likely, he won't be faithful. Or he won't be religious. So no perfect man don't exist. Perfect gas don't exist. Perfect human being don't exist. Is that okay? So you know what I mean by perfect gas, ideal gas now. Ideal gas is a perfect gas, which does not really exist in real sense. Though some gases are very close to being ideal than others. Is that okay? So what are the properties of ideal gas according to Kinetic theory? Let me make it bigger. Can you start reading for me?
Ideal gas molecules have no volume.
Read it from the top.
Postulates or assumptions of kinetic theory for an ideal gas.
Yeah, go on.
Ideal gas molecules have no volume.
What does that mean? They have how do you put in back? They have what? Zero particle volume. Let me put the way they put it. They have what?
They have no volume, zero particle.
Zero particle volume. Can you read it? What does that mean?
This implies the actual volume of the gas molecules is negligible compared to the volume of the containing vessel.
Thank you. Stop there. In your room, in the way you stay now, maybe you stay. All the air in your room, if I pack them, you know a normal biro, the cover of a biro, the cover of a pen, your biro. Am I right? If I pack all the air inside your room, I can pack them into the container of your biro. Now compare the volume of that container, the cover of your biro, compared to your whole room. So if you pack all the gases in your room together, the volume they occupy, they're saying that it's almost zero. But Adiga is saying that the volume is zero. Is the volume actually zero?
Mm.
Hello, Adiga, can is saying that when you pack all the gases in your room,
Yes.
they have no volume at all. Are you saying they don't have any? They have volume, of course. The volume may be very, very small, but not. You can't say they have zero volume. Do you agree to that?
Yes.
Zero volume means they don't exist. That's not correct. Totally correct. But I saying that for a gas to be perfectly ideal, the gas has no volume at all. That is, it's telling that the volume is zero. It's not telling that. It's not telling that the volume is zero. We know that gas don't have zero volume. We know they don't have zero particle. We know they don't have that. But ideal gas must have what? Zero particle volume. Now to get that now look at it. Based on that, if you compare the following gases, zero particle volume. I want to explain that to you so that you can get it. Kinetic theory, ideal gas. Now look at if you have hydrogen molecule here. Hydrogen molecule. Here you have carbon dioxide molecule. Here you have chlorine molecule. Here you have SO3 molecule. SO3 molecule in the same volume. Which one is closest to the ideal? Based on what I just said now, they said they have zero particle volume.
Mm.
Which one is the closest to ideal gas? Hydrogen. You know why?
Hydrogen.
Hydrogen gas are so tiny. It's the smallest gas now. Am I right? It's so like
Yes.
hydrogen that if you want to pack it, it may not occupy more than this space. All the gas in there, maybe you occupy this space. But then you can you now look at this volume compared to the whole volume. By the time you pack all the gas inside this container together, look at the volume they occupy. You pack them so that there's no space between them. That's what I mean by that. So is that okay? Do for CO2. CO2 may occupy this volume because it's bigger than hydrogen gas. Do for chlorine. Chlorine may occupy this volume. Do for SO3. SO3 may occupy this volume. So which of them is it? Which of them? All of them are not ideal. None of them are zero particle volume. None of them. But now,
Yes.
which are very close to zero? Hydrogen.
Hydrogen.
Thank you. So this way, you can say that ideal gas. What can you say? Conformity to ideal behavior decreases. This way. Conformity to what? Ideal gas behavior decreases. Do you agree to that?
Yes.
The bigger the size of the gas, the less it conforms to ideal behavior. Because if the gas is bigger in size, then the particle will no longer be zero. The particle will become what? More less negligible. Do you agree to that? Before you know, it won't comply again. So ideal gas does not exist. But gases which are very, very small in size are the best ideal gas. Do you agree to that? They are very close to it. They are very, very close to it. But do you get the concept?
Yes, sir.
That's one. Number two. Yeah, number two. Number two.
There are no intermolecular forces present between ideal gas molecules.
But we know that real gases, this thing that they are for ideal gas, but we know that real gases have intermolecular forces. Let's do that. Yeah. I'll tell you some gases. Tell me the. So this is point one, ideal gas, zero particle volume. This is zero particle volume. Zero particle volume. Number two, you said no intermolecular forces, Abi. No intermolecular. So you have to read the two notes together. Do you get them? I'm explaining here. Do you agree?
Yes,
That
sir.
you have to read together. Now look at this. Hydrogen, nitrogen, chlorine. This is the gas. Then again, steam. Let me see. Hydrogen fluoride. Which of these does not? All of them. These three guys, they are non-polar. They have ID forces only. Remember this? Non-polar,
Yes.
ID forces only. So they have the weakest. So they are very close to ideal. Do you agree to that?
Yes.
ID forces only, because ideal says they don't have any, but this guy have. But what they have is very, very weak. So they are very close to ideal.
Intermolecular forces.
If I now consider this guy now, ammonia, hydrogen fluoride, water, this is the guy. They are polar with hydrogen bonding. With what? Hydrogen bonding. So this guy, they are less ideal compared to the first guy. Do you agree? This guy, less ideal. Am I
Yeah.
right? Yeah,
Yes.
closer to ideal. Closer to ideal. Therefore, the weaker the forces between your molecule, the more ideal behavior you are showing. Because ideal says there are no forces between your molecules. So the one that have the strongest intermolecular force deviates most from kinetic theory behavior for an ideal gas. Is that okay? This guy, they
Yes.
deviate more. They deviate most from kinetic theory postulates for what? For ideal gas, for an ideal gas. This guy, they conform more. They conform more. Or what? Or deviate less. From what? From kinetic theory. Or from ideal, just as from ideal behavior. Nobody is 100% ideal, but these ones
Mm.
are still closer than the other one. Is that okay?
Yes.
I'm sure that makes sense. So
Yes.
good. Let's go back to our notes. So I've done number 3. Yeah.
Collisions between ideal gas molecules are perfectly elastic.
Are you doing physics?
Sir?
You do physics in your IGCSE.
Yes.
What that means is that when they collide, they don't lose any, they don't gain energy. That's not true. When they collide, they make sound somehow. When gases collide, when air is bruising and there's
Mm.
wind blowing, don't you hear sound?
We
They
do.
collide with each other, they make sound. In the process, they are losing energy because they are wasting part of the kinetic energy in form of what? In terms of heat energy and sound energy. We
Mm.
are saying that for ideal gas, when they collide, they don't lose energy at all. We know that's not true. So again, smaller gases, when they collide, they lose less energy. Bigger gases, when they collide, they lose more energy. Again, the smaller the molecules of the gas, the more it conforms to ideal behavior. Is that okay? Anyway,
Yeah.
collision between gas molecules are perfectly elastic. What that means that energy is not, should we say momentum? What's momentum in physics? Mass time velocity, am I right?
Yes.
Momentum is conserved. Momentum
It's conserved.
or energy is conserved. When they collide, they don't lose energy. Therefore, they continue to collide indefinitely. You know what they are saying? They're saying that I think they just continue colliding with each other. They don't stop colliding. You say that's not true in real life. When they continue colliding, some of the energy will waste in form of heat energy and sound energy, right?
Mm.
Therefore, they slow down over time. But here you are saying that no, they never slow down. They continue to collide with each other. But as they collide, they don't lose it. We don't have to cater for that to counter that area. We not say, okay, when they collide, they don't lose energy. That's not true. How can you say a vehicle just continue to move indefinitely? Something is slowing down. When the sun will slow him down, the boy guy will stop it someday. Do you get the point now? So that's how I
Yeah.
do. Number 4, call.
Ideal gas molecules behave as rigid spheres.
They don't repel each other. They don't attract each other. Everybody go on his own. As if they don't know each other. They collide, they don't attract, they don't repel. Do you get everybody go on his own? Do you get the point now? Number
Mm.
5,
Molecules of an ideal gas move randomly in all directions and in straight lines.
that's it. Yeah, go on.
The kinetic energy of ideal molecules is directly proportional to the absolute temperature in Kelvin.
The higher they move, the greater their temperature.
A lot, and you're like, okay, do you have a private tuition? Don't you have? Do you have? And yes, Ajiro Tech do have a private tuition. So by my right, you can see that we have for the EdExcel and Cambridge IGCSE, and yes, we do have for all subjects. Okay, all subjects. Okay, the popular ones that's always been in demand is mathematics, English language as a second language. Okay, we have physics, we have biology, we have chemistry, and we have um, the flagship, which is ICT, just here and there. We also have business studies. So if you're interested for a private tuition, I think all you have to do is send an email to the sales team at ajirotech@gmail.com, and they would reply to you, talk about your time zone, talk about, and the fee is really quite affordable. Really, it's really quite affordable. It's when you look at it across other tutoring service, I think this is the one that's quite affordable, and you get the very best of service. We also have for the E levels as well, and also for the EdXL. So we have for the Cambridge E levels and EdXL E levels. Okay, and we have also across the subject mathematics, which is usually the hot cake when it comes to E level, mathematics and chemistry, and then biology. These are usually one of the ones we have in demand always, all the time, even physics, for E level. So all you have to do, if you're watching this right now and you are interested for a private tuition, then you can do yourself a solid, okay, and send an email to the sales team at ajiro@gmail.com, and they'll reply to you. And the good news about this is, what I've discussed with the sales team is, we've tried as much as possible to see how we can subsidize the amount according to countries, so it doesn't really look very, very heavy. Okay, so this is really important. Yes, we do charge in pounds, but again, we try to be as much as possible considerate to your countries, and we don't just skyrocket the price. No, because at the end of the day, we know how it feels, and we really want you to actually get the best of service, and again, be able to afford it from the comfort of your home. So again, Ajiro Tech private tuition is currently ongoing. You can enroll yourself for the IGCSE, and then for the E levels. Again, for the IGCSEs, these are the subjects, and for the E levels, these are also the subjects. So again, what are you waiting for? Just send an email to the sales team. If you're an IGCSE student preparing for IGCSE, if you're watching this in 2025, watching this in 2026, watching this in 2027, we're currently ongoing, and this is actually a good time for you to actually explore, and then get it tailored to your own needs. So trust me, you don't want to miss out.
After the what? The kinetic energy. How do I know? Temperature, high temperature, high what? High velocity. Am I right? Or high speed. And energy. Can you hear me?
I can now. It was breaking.
Can we, can you? Okay, what it was breaking before? Okay, so
Yes.
temperature,
Mm-hmm.
greater speed
Mm-hmm.
or velocity. And KE equals to what? Half mv squared. Do you agree in physics?
Yes. Mm-hmm.
So when you increase temperature, the V will increase. Therefore, kinetic energy will increase. Is that okay?
Mm-hmm.
Now is it that the kinetic energy of the molecules and temperature, they are directly proportional to each other. Is that okay? And
Yes.
finally, what's number 7 now?
The pressure exerted by the gas is due to the collisions between the gas molecules and the walls of the container.
That one is true. That one is true? Is that okay? Good.
Mm.
That's fine. Now, I can prove this point to you. There was here they asked this question. This one. Zero particle volume. Do you have data book? Do you have data book? Have I sent you data booklet? Have you downloaded it? Data booklet.
Yes, you have.
Thank you. Is it something you can open?
Yes, let me open it.
Thank you. So let's prove this number 2. Number, let's prove by calculation. To prove that the actual volume of gas is what? Is negligible compared to the volume of what? Of content. Let's use argon as an example. Argon. We are using argon as an example. Now, what's atomic
Okay.
radius? What is atomic radius of argon? Can you check your data booklet? You know where to check it. Have you opened
Okay.
it?
Yes, I have it loading.
There's a page there that they show atomic radius. Locate it.
Okay.
It's not if after I don't know. They show atomic radius.
There should be a page, atomic radius. Atomic and ionic radii.
Thank
Okay.
you. Yeah, what's atomic radius of argon? Atomic radius of argon. Locate it there. It should be there.
Okay.
0.192 nanometers or something like that.
Of
Locate it.
argon.
And yeah, it's there. AR.
It's written period 3, group 2. Okay, argon. Found it here. AR.
0.192 nanometers.
0.190.
190. I try. 190. Is that the radius? That's radius.
Yes.
Now, can you an atom? What can you say? Which shape is atom, or which structure is it? Atom is a sphere. Do you agree? Atom is a sphere. I mean, it's like a ball, right?
Yeah.
Good. Yeah, let's go now. Can you find the radius of one atom? Find radius of one atom of argon. Can you find? How do you find it? I mean, did I say radius? I mean volume. In that year they said volume of a sphere equals to 4/3 pi r cube. They give them in the question. So let's find the volume. We have 4/3, 22.7. What radius? 0.190 times 10 to the power minus 9 meter 3. Do you agree? I want to get the meter cube.
Where is times 10 to the power negative 9 coming from?
I'm converting nanometer to meters.
Oh, okay. Okay.
Nanometers to meters.
Yes.
Yeah. Can you calculate it? Can you calculate this in your calculator? Can you calculate it?
Okay.
Let me see if I can do it on my phone. I don't have my calculator here. Four divided by 3 times 22/7.
Getting
times. What do you get?
2.87 times 10 to the power negative 29.
Yeah, it's correct. Negative 29 meters square. Am I right?
Yes, meters
This
squared.
is the volume of one single atom. Do you agree?
Mm-hmm.
I wonder, how do you find the volume of 1 mole of argon? This is
We
the volume
say
of one single atom. What would that be the volume of 1 mole of argon?
we say 1 is equal to 6.02.
Thank you so much. So this is one atom. This is for one atom.
Yeah.
So 1 mole now, 1 mole, which is equal to 6.02 times 10 power minus 20. No, 6.02 times 10 power 23 atoms should now be 2.87 10 to the power minus 29 times 6.02 10 to the power 23. Yeah, what do you get here?
Okay, I'm calculating.
What I calculate is it the real volume or ideal volume? This one I calculate. Is it the real volume or ideal volume? Be careful. They gave the radius, the actual radius of atom. What I calculate is it the ideal volume or real volume?
The real volume?
Thank you, because they give you the real radius. They said the radius.
Yeah.
So what I calculate is not ideal volume. You are calculating the actual volume of 1 mole of gas. You use argon. What do you get?
I'm getting 0.0000.
Tell me in standard form, please.
1.73 times 10 to the power 5 negative 5
meter cube. Can I take it to dm cube? What we do? How do you convert the meter cube to dm cube? So times 1,000 now.
times
Now
1,000.
in dm cube. So what do you
Okay.
get?
0.017.
0.0173 dm cube. That is the actual volume
Uh-huh.
of 1 mole
Oh,
of
oh.
argon gas. Do you agree?
Yes.
What is the ideal volume of 1 mole of gas at RTP?
Zero. It's zero.
I won't tell you. You are going to get the answer. I won't tell you. What is the ideal volume of 1 mole of gas under room conditions? Ideal volume.
It has no volume. Ideal gases have no.
I understand. I mean, when the gas, okay, I got it, you're right. But under room condition, what is the volume of 1 mole of gas under room condition?
24 dm cubed.
So 1 mole of gas under room conditions occupy 24 dm cube, whereas the actual volume is 0.0173 dm cube. Do you get the point now?
Oh,
1 mole
yeah.
of argon gas under room condition actually occupies what? 24 dm cube. But the actual volume, if you can pack all the gas inside that dm cube together, this volume they occupy. So you now say 1 mole of gas occupies 24 dm cube at RTP. Are you there? Now,
Yeah.
can you now compare this? Is it very negligible or not? Versus 24 dm cube. Am I right? Let's see percentage of 0.0173 over 24 times 100. What do you get? We want to see the actual volume compared to the volume of the container under room condition. For
Zero,
argon, yeah,
0.072.
percent.
Mm-hmm.
Now take that to, let me take a fraction. What does that mean? It's like 72 over, well, 1, 2, 3. That's 72, 0.072 over 100. Am I right?
Yes.
Take it to whole number. Shift like how many times you shift the figure? How many times will you shift the decimal place? Let me write it down. 0.072 over 100. 3 times, what will it become? 72 over what? 100,000. Do you agree? Is that correct? Is that correct?
Yes, sir.
So if the container is 100,000 dm cube, the actual volume occupied by argon gas will be what? 72 dm cube. Do you get the point now?
Mm-hmm.
So it's actually negligible. Is that
Yes.
okay? So
Yes.
72 out of 10,000, 100 out of 100,000 is really negligible. So that this is a question from Gideon said, this is to prove to us that actually the actual volume of any gas compared to the volume of the container under room condition is very negligible. Argon is bigger in size. If you now use helium, it will be smaller. Do you agree?
Mm.
So this is argon. This is argon, right? If you use neon may be like maybe, I don't know, maybe 44 over 100,000. I'm just assuming. Am I right? If you now use helium, maybe it become, maybe I don't know, become 20, 28 over 100. Can you see now?
Yes.
As the atom are becoming smaller and smaller in size, they are tending towards being an ideal gas. Ideal gas says the volume should be 0 over 100,000. Am I right? That's what the ideal gas says. So the volume should be 0 over 100,000 because the 0 is 0. It doesn't have any volume. Do you get the point now?
Yes.
But here we know that as by decreasing the radius of the gas, argon, neon, and helium, they are all in the same group. We know that if the radius of argon is 0.190, what's the radius of neon? Is it there? Check that, please. Neon there?
Neon, I couldn't find it.
It's not there. Okay, leave it. So we know that neon should be smaller. We know that, right?
Mm-hmm.
What about helium? It should be smaller still. Am I right?
Mm-hmm.
So the smaller the particle of the size, the more it behaves like an ideal gas. We are done with that. So that's all this. You can, in example, you have to say only two. The most important two are these two. These three are the most important three. You have to say the first three guys. They are the most important three. condition is perfectly elastic. No intermolecular force between them. And so under what condition do gases behave like an ideal gas? Yeah, read it. Can you read?
Conditions under which real gases approach ideal behavior.
They will
High
never
temperature.
ideal behavior. You are doing math, am I right?
Yes, sir.
Ideal behavior is at infinity. They are tending towards it. They will never get there.
Mm.
No gas will ever get to ideal. No gas will get there, but they are tending towards it. They are moving closer to it. Under what condition? Under high temperature and under low pressure. What do I mean? Look at this. What does low pressure mean? Large container, small particles of gas. Am I right? Small particles of gas. Is that not low pressure?
Mm.
Now, when you do this, when you do low pressure, what does that mean? The gas particles are very far apart. Therefore, the intermolecular force be very, very weak. Do you agree between them? Very, very weak. Do you agree to that? When the
Yes.
particles are very far apart, the force between them become what? Very, very weak. Do you agree? That means they are behaving almost like an ideal gas. When the temperature is high also, the speed will increases. And now, that will agree with number 5 point. Look at number 5. They move randomly in all directions and in straight line. When increase temperature, they begin to move randomly in all directions. Do you agree to that? When you decrease
Yes.
pressure, the force between the particles will be very, very small. Do you get the point now? And therefore, it behaves like an ideal gas. So you have to remember that real gases, they want to behave like an ideal gas when temperature is very high and when pressure is very low. Do you get now? At
Yes.
low temperatures, at low pressure, the gas molecules are very scattered apart. Therefore, the force between them will be very, very weak. They are behaving like an ideal gas. At high temperature, they are very, very scattered abroad also. But at low temperature and high pressure, they deviate from kinetic theory. Do you agree to that?
Mm-hmm.
At low temperature, and can you explain that? Why? Because at low temperature, the speed of the gas molecule will decrease.
Mm-hmm.
They come closer together. Because they come closer together, intermolecular force will no longer be negligible. It will be pronounced. Do you agree? The closer they are, the stronger the force between them. Do you agree?
Yes.
So if you do them at low temperature, the gas molecule will come closer together and force become real among them. Is that okay? So I've explained this to you before. Pressure and volume, inverse proportional, volume and temperature. So generally, when you combine all these together, what this means is that when you have low volume, high pressure, increasing volume, decreasing pressure, very high volume, very low pressure, greatest volume, lowest pressure. Is that okay? Pressure
Mm-hmm.
and volume are inversely proportional. So you can introduce a constant K. K is a constant here. Therefore, K equals to PV. What does that mean? The product of the pressure and volume of a gas is constant. Camila, do you understand that?
Yes, sir.
Pressure and volume are inversely proportional. We introduce a constant K, which is this. Then K equals to PV. That means the product of pressure and volume is a constant. That means P1V1 equals to what? P2V2 equals to what? P3V3, etc. Is that okay? Then look at this. Volume and temperature are when you increase temperature, pressure want to increase.
Mm-hmm.
To keep the pressure constant, you must increase the volume. I
Mm-hmm.
say volume and temperature be really proportional when pressure is constant. When you increase temperature,
Mm-hmm.
the molecule they will collide more frequently and the pressure will want to increase. But if we want to keep pressure constant, what do? We increase the volume. So if you increase temperature, you must increase the volume if
Mm-hmm.
pressure must be kept constant. Do you get the concept?
Yes.
So V and T are the proportional. V equals to KT, K equals to V over T. That means if we divide volume and temperature is always constant. Is that okay?
Yes.
Then if you combine all these together, that means PV over T equals to constant. Combine the three of them. At the end of the day, PV equals nRT. Where P is what does P? Let me see if I define it. Yeah. What does P represent? P represent what? Pressure exerted by the gas. Pressure exerted by the gas. In calculation, it should be in what? In Pascal, which also means Newton per meter square. You are in calculation, we have with units. Then V equals to volume. Don't say volume of the gas, so volume of the containing vessel. A gas does not have its own volume. It fill up the whole volume. Do you agree to that? So volume, don't say volume of the containing vessel. In calculation, must be in meter cube. I'll prove it to you now. And don't forget that 10 to power 3 dm cube equals to 1 meter cube. And 10 to power 6 cm cube equals to 1 meter cube. So to go from cm cube to meter cube, divide by 1 million. To go from dm cube to meter cube, divide by 1,000. Is that okay? So
Yes.
pp, what does n means? Amount of gas in moles. Amount of gas. Amount of gas in what? In moles. Then what does R mean? Universal gas constant. Universal gas constant. The unit is, the value is 8.31. It's in your data booklet. Joules per mole per Kelvin. Then T is what? Absolute temperature in Kelvin. Absolute temperature. And the unit is what? Is Kelvin. I'm sure this makes sense.
Yes.
So this is now, how do we get the value of R? From PV constant RT. If you consider 1 mole of gas, that is N equals to 1, from here, I'm talking about here now. If you consider 1 mole of gas, N will be 1 at standard temperature of 0 degrees Celsius, which is 273 Kelvin. I will do that again. If you consider 1 mole of gas at standard temperature of what? 0 degrees Celsius, which equals to 273 Kelvin, and our standard pressure of what actually is 101325 Pascal. They will tell you approximately 101,000 Pascal. They will tell you 101 kilopascal. Do you understand that? The actual value is 101325 Pascal. But they will tell you approximately 101,000 Pascal. Is that okay? Which means 101 kilopascal. Do you agree?
Yes.
So, and the volume of gas, what's the volume of ideal gas at STP? 20.4 dm cube. Compared to meter cube, that's it. So at the end of the day, what will be your value of your R? 8.314 Newton meter square, Newton meter per mole per Kelvin. Newton times meter, that is force times distance. Force times distance in physics is what? Is work done. And unit of work is what? Is joule. So it will be 8.31 joules per mole per Kelvin. Don't forget, your pressure must be in Pascal.
Yes, sir.
Your volume must be in meter cube. N is amount of gas in mole. R is universal gas constant. T is in temperature in Kelvin. Is that okay? Let's go. So this is, I've defined it here for you again. So from here, number 1, you can use PV constant RT to find the mole of gas or anything they want to find. Number 2, what does N means? Mole. In terms of masses, what is mole? Mole equals to, so I'm converting this to this now. Thank you. Mass over what? Relative molecular mass. From here now, can you make a mass substitution formula? From number 1, I go to number 2. For that number 2, I now go to MR equals to, I now go to this now. MR equals to MRT over PV, where M equals to mass in grams. In grams, so not kilogram, because mole is always mass in grams over molar mass. Don't forget that. Mole is never kilogram. Mole is mass in grams over molar mass. So where M equals to mass in grams, MR equals to relative molecular mass of the gas. Is that okay? So you can use this equation number 1 to find mole. Use that to find the molecular mass of the gas. Is that okay? So you get the point. I'll give you a question now to get it. Now let's go. Number 3. From MR equals to this, can you find the expression for density? What is density?
That's
Mass.
all.
So we want to change that. We want to bring it out. So there's a mass here, there's a volume here. So can we bring it out? It now become what? MR equals to what? M over V, RT over P. What's that? What's that M over V? That means MR equals to D, where density, D equals to density. dRT over P. It now become density equals to what? MRP over RT. Where what would be the unit of the density? Don't forget the mass is in grams.
Mm-hmm.
Volume is in meter cube. Therefore, you need to be what? Gram per meter cube. Do you agree?
Yes.
Good. That's good. So now we are done with that. We'll do calculation now. Don't worry. Now, for an ideal gas, come and see. This is I wrote here. What is a PV? PV is constant. Do you agree? PV does not change at all temperature. Is that okay? PV
Yes.
does not change at all pressure. Come and see now. If you plot a graph of PV of an ideal gas against P, you get a straight line. Because we say PV is always a constant value. Do you agree?
Yes.
If you come and see it again, PV is constant. Look at it here. PV equals to K.
Mm-hmm.
The product of pressure and volume is always constant. For example, pressure can be 100, volume will be 1. Pressure 50, volume is 2. Pressure 25, volume is 4. 20, 5, 10, 10. Do you get the point now?
Yes.
As one is decreasing, the other will be increasing.
Mm-hmm.
Is that okay?
Yes.
So the product of pressure and volume is constant, such that as one is increasing, this is volume, this is pressure. So guys, it's constant. PV is
Mm-hmm.
come and see the graph now. So do you agree that's it? Do you agree this graph is right? Do
Yes.
you agree that this guy is for ideal gas? Ideal
Yes.
gas should not change, it's constant. So this is ideal gas. We now plotted PV against P for 3 other gases. Gas A, gas B, gas C. Look at the graph we obtained for them. Which of the 3 gases is closest to the IV behavior, A, B, or C?
A.
Thank you. Followed by
Followed by B, then C.
which one debate most? C. So now let's go now. A could be hydrogen gas. You know why? Hydrogen gas has the weakest intermolecular force. B could be chlorine. Chlorine contains more electron than hydrogen, therefore stronger IDID than hydrogen. Is that okay?
Yes.
C may be ammonia. Ammonia has hydrogen bonding.
Mm-hmm.
Of course, we have said that the one that has the strongest intermolecular force is one that deviates most from kinetic theory.
A lot, and you're like, okay, do you have a private tuition? Don't you have? Do you have? And yes, Ajiro Tech do have a private tuition. So by my right, you can see that we have for the EdExcel and Cambridge IGCSE, and yes, we do have for all subjects. Okay, all subjects. Okay, the popular ones that's always been in demand is mathematics, English language as a second language. Okay, we have physics, we have biology, we have chemistry, and we have the flagship, which is ICT, just here and there. We also have business studies. So if you're interested for a private tuition, I think all you have to do is send an email to the sales team at ajirotech@gmail.com, and they would reply to you, talk about your time zone, talk about, and the fee is really quite affordable. Really, it's really quite affordable. It's when you look at it across other tutoring service, I think this is the one that's quite affordable, and you get the very best of service. We also have for the E levels as well, and also for the EdExcel. So we have for the Cambridge E levels and EdExcel E levels. Okay, and we have also across the subject mathematics, which is usually the hot cake when it comes to E level, mathematics and chemistry, and then biology. These are usually one of the ones we have in demand always, all the time. Even physics, for E level. So all you have to do, if you're watching this right now and you are interested for a private tuition, then you can do yourself a solid, okay, and send an email to the sales team at Ajiro@gmail.com, and they'll reply to you. And the good news about this is what I've discussed with the sales team is we've tried as much as possible to see how we can subsidize the amount according to countries, so it doesn't really look very, very heavy. Okay, so this is really important. Yes, we do charge in pounds, but again, we try to be as much as possible considerate to your countries, and we don't just skyrocket the price. No, because at the end of the day, we know how it feels, and we really want you to actually get the best of service, and again, be able to afford it from the comfort of your home. So again, Agile Tech private tuition is currently ongoing. You can enroll yourself for the IGCSE and then for the E levels. Again, for the IGCSEs, these are the subjects, and for the E levels, these are also the subjects. So again, what are you waiting for? Just send an email to the sales team. If you're an IGCSE student preparing for IGCSE, if you're watching this in 2025, watching this in 2026, watching this in 2027, we're currently ongoing, and this is actually a good time for you to actually explore and then get it tailored to your own needs. So trust me, you don't want to miss out.
So can you now see now that these three gases, we can predict that A is the one that have the weakest intermolecular force. Am I right?
Mm-hmm.
A has, then C has the strongest intermolecular forces. So C deviate most. A is one that deviate least among all of them. So you get the point now. That's
Yes.
one. This different. Then now what if we do this now? Look at it. Kinetic theory. What does this mean? Mathematics, please. I don't know how good are you at math. Pay attention. What does this mean? P and 1 over V are directly proportional. Do you agree? That's what it means?
Yes.
You can do you agree that what it means? P
Yes. When
and
one
1
and
over
one
V
other
are
decreases.
directly proportional.
Mm-hmm.
Am I right?
Yes.
What about the next one? What does it mean? P and V are inversely proportional. Is that okay?
Mm-hmm.
Are you sure? Now look at this one again. We now do the same gas. This ideal gas, of course. Oh, this ideal gas. We now do gas A at different temperatures. Gas A at T1, gas A at C2, gas A at the same gas A at T3. When do gas behave like an ideal gas? Is it under low temperature or high temperature?
Under low temperature.
Are you sure? When the gas operates under low temperature, the molecule will come together, they will turn to liquid, they will deviate from ideal gas. So they come and see what I wrote here. I just taught you today, you will not remember it, but you will learn it.
Okay.
You come and read what I put here. No. Yeah, look at you. Can you read it?
Oh, high temperature and low pressure.
You have to remember. Is that okay? Me,
Yes.
I always remember high temperature. I know that when they have high temperature, they have more energy. And
Mm-hmm.
can you say molecules have more energy? That they have more energy. So under high temperature, they always have more energy. Do you get the point? So,
Yes.
so now come and see these three guys. Yes.
Who said it is time?
Okay. Yeah. Now look at this. Now, which of the temperature do you think with the highest? T1 is the highest. Do you agree?
Mm-hmm.
But T1 is the closest to ideal. T3 is the lowest temperature. Do you agree?
Mm-hmm.
At T1, which is the highest temperature, they are very close to ideal. At T3, they are very far from ideal, low temperature. Do you get the point?
Yes.
Are you sure you get what I'm saying here?
Yes, I do.
Good. Now look at this one. Now we now plotted volume and temperature in Kelvin. This is not like this one is not. If you do, it's not correct. It's not correct to say like this. It's not correct like this. Though. It's not correct. You know why? Ideal gas don't have zero volume at 0 degrees Celsius. Ideal gas will only have zero volume at 0 Kelvin, which is never attainable.
Yes, sir.
Ideal gas have zero volume at zero. What's 0 Kelvin? Minus 273 degrees Celsius. Do you agree?
Mm-hmm. Yes.
So ideal gas have zero volume at 0 Kelvin. Or
Mm-hmm.
ideal gas have what now? They have zero volume at what? Minus 73 degrees Celsius, right?
Mm-hmm.
Now,
Yes.
Why is it not possible to get to 0 Kelvin? Why is it not possible? From what you have learned in real life, is it possible to get 0 Kelvin? Gas will have
No.
condensed and gone to solid before that time. Do you agree?
Mm-hmm.
Take gas to minus 80, minus 200. But then get turn to liquid. You can't remain a gas again. It's not possible. So
Yes.
minus 0, minus 23 degrees. Okay, I think it's here. Can you read it? Oh, good. It's here. Can you read?
Absolute zero is the lowest possible temperature where heat energy is absent in a substance. It is the temperature at which the motion of all particles in a substance would come to a complete stop and the substance would have no energy. Absolute zero is defined by the laws of thermodynamics and can be calculated by extrapolating the volume absolute temperature graph as shown above.
Thank you. With this guy, come here. It's supposed to get this. Okay, yeah, go on now.
In practice, real gases do not attain this temperature. Most gases liquefy and solidify before this temperature and would have ceased to be gases.
I want to write liquefy. That's not liquid. It's liquefy. Liquefy. Q. Liquefy. It turns to liquid. So you cannot have a gas that will have 0 Kelvin. It's not possible.
Mm.
To the liquid and gas. Is that solid and liquid? Is that solid, liquid and solid? It's not possible. So it cannot remain a gas up to that temperature. It's not possible. So we are saying that 0 Kelvin is just imaginary, it's just an imagination. It can never happen in real life. It's only for ideal gas.
Yeah.
If an ideal gas can exist up to that temperature, then the temperature becomes zero. I mean, the volume becomes zero. Is that okay? Good.
Yes.
Now let's go. Read. Can you read? Helium, neon, argon, and krypton. Number of electron increases. Strength of IDID forces increase. Deviation from ideal gas behavior also increases. Is that okay?
Yes.
I want to write also increases. Yeah. Now that these guys, look at the one I gave again. Cl2HCl Cl2 have IDID forces only. HCl
Yes.
is polar, so it has PDPD in addition to IDID. And
Uh-huh.
PDPD is stronger than IDID.
Yes.
HF has hydrogen bonding between its molecule, which is the strongest. Is that okay? Therefore,
Yes.
these three guys, HF deviates the most, Cl2 deviates the least. Is that okay?
Yes.
So now can you read this too now?
Deviation from ideal behavior at lower temperature. When temperature decreases, the average kinetic energy of gas molecules decreases. Molecules slow down and tend to come closer. Intermolecular distance decreases and intermolecular forces thus become significant and no longer negligible. As temperature decreases further, most real gases actually liquefy or condense and cease to be gases, thus deviating completely from kinetic theory postulates. The stronger the intermolecular forces, the easier the gas liquefies and the greater its deviation from ideal gases.
Do you understand that?
Mhm.
Yeah, now read the second one.
Deviation from ideal behavior at higher pressures. At high pressures, a large number of gas molecules are forced to come together into a smaller volume and intermolecular distance decreases. Under this condition, intermolecular forces are no longer negligible and the concept of zero particle volume no longer holds. The volume of the gas molecules relative to the volume of the container becomes significant.
It's no longer negligible. Do you get that? So I'm telling you why gases deviate from ideal theory under what? Under low temperature and under high pressure. Is that okay? Now,
Yes.
types of crystalline solid. We have discussed this now. I'll just go over it for you. These are the ones we have discussed initially. What's going on? Let me see it a bit. Yeah, it's saved. Type of crystalline solid. It may not follow the other. Can you just read fast?
Okay. Types of crystalline solids. A crystalline solid consists of repeating three-dimensional patterns or lattices of particles, ions, molecules, or atoms, which are arranged in a highly ordered microscopic structure. The particles that make up a crystalline solid exist in a regular, well-defined arrangement. The smallest repeating pattern of crystalline solids is known as the unit cell. Unit cells are the
I
what,
like,
sir?
I like bricks.
They are like bricks in a wall. They are all identical and repeating.
Mhm.
Non-crystalline or um
Amorphous. Amorphous solids.
solids, and non-periodic order of particle arrangement. Examples include glass, polymers, gels, wax, and many plastics.
Those ones are not crystalline. They are not crystalline. They just arrange themselves anyhow. Do you get now? They are called amorphous. Non-crystalline means amorphous. Please do that. Non-crystalline. Let me be sure you understand this. Give me crystalline allotropes of carbon. Diamond, graphite, and fullerene. Fullerene. Is that okay? Pokeball. Give me non-crystalline forms of carbon that you know. Coal, coke, charcoal. They don't have a definite shape. Coal, charcoal. They don't have a definite shape. They are amorphous form of carbon. They don't have a definite shape that they follow. But diamond, graphite, and buckyball, they have a definite shape that are repeating. They call them crystals. Is that okay?
Yes.
Now look at it now. Crystalline solid. How many do we have? We have giant metallic, giant ionic. We now have molecular. Under molecular, we have giant molecular. We have simple molecular. Now, hydrogen bonded solid are also simple molecular. Under they have stronger forces. Is that okay? So yes. I'll assume that these two, I can classify these two together. These two, I can call them one. I can call these two one, that they are one. Simple molecular and hydrogen bonded, I can say they are one. Is that okay? But they're both simple covalent. But in hydrogen bonded is simple covalent. Simple molecular are also simple covalent. But hydrogen bonded, in addition to having ID or PD also has what? Hydrogen bonding. Is that okay? Give me an example of solids that are purely hydrogen bonded. Water, ice, one. What about DNA? Is it hydrogen bonded or not? DNA in biology?
Yes, it is.
What about proteins?
Proteins, they have hydrogen bonds.
Do you get the point now?
Yes.
So we have hydrogen bonds that stabilize their secondary structure. Remember that in your biology. Hydrogen bonds stabilize secondary structure. Do you get it? So my point is that some molecules have hydrogen bonding. Ice, protein, DNA, etc. etc. Is that okay? Now let's go.
Yeah.
Metallic solid. Can you read fast? So this one we should take another 10 minutes. Let's go to the top. Yeah, start.
Metallic solids consist of cations and delocalized electrons. Are mostly solid since they have giant metallic structure with strong metallic bonds between the cations and the sea of electrons. The presence of electrolyzed electrons
of delocalized electrons.
The presence of delocalized electrons makes them good electrical and thermal conductors.
Thank you.
Most metals are insoluble in water. Some reactive metals, however, dissolve or react in water to form an ionic solution which conducts electricity.
Metals like cobalt, like copper, like silver, like gold, like iron, they don't react water. Is that okay? There's some reactive metal like all these group 1 elements, they react water and produce hydrogen and produce metal hydroxide. Is that okay? Good.
Yes.
So this is a metal. Is that okay? I'm done with metallic structure. Now next one.
Giant ionic solids consist of alternating positive and negative ions held together by strong electrostatic forces. They are mostly solids with characteristic high melting points. They are poor electrical conductors in the solid state, but good conductors in molten liquid state, and when dissolved in water, aqueous state.
Why are they not conductor in solid state? The ions are not mobile. They are not free to move. They are strongly held together. But when are the ions free? When they are dissolved in water or when they are molten. Is that okay?
Yes.
So this is a unit cell of sodium chloride. So the smaller one will be what? Which one will be smaller? Which one will be bigger? Sodium has 3 shells. After losing the outermost electron, the outermost shell is also lost. So sodium ion has 2 electron shell. Do you agree? 2,
yes.
8. Chloride ion was 287 before. After gaining 1 more electron, number shell is still big now. Can you see that this is chloride ion minus plus? Is that okay? So
yes.
You can now see Na plus Cl minus, Na plus Cl minus. They must be alternating. So they can also draw the one here. They said you should draw this. They said you fill it up 1 mark. Na plus Cl minus, Na plus Cl. It must be alternating with each other. Is that okay? So a unit cell of NaCl. Can you read on?
A unit cell of NaCl. Considering the crystal of sodium chloride as a whole, each sodium ion is bonded to 6 chloride, and each chlorine is bonded to 6
Each chloride,
and each chloride is bonded to 6
sodium
sodium
ion.
ions with strong electrostatic attractions or strong
Let,
ionic bonds.
let me show you that. Let me show you what that means. Structure of sodium chloride. I want to see that structure of sodium chloride. I will copy it. This. Let me copy it. That's only you can understand this. Now you're going to focus on something here. Let me take this one. I prefer this one. Now look at it. Pay attention. Focus on this guy. Can you see my cursor?
Mm-hmm.
Now, let's say that is sodium ion. How many chloride are surrounding? There's one chloride behind it. Am I right?
Yes.
That red guy, chloride. What about the one in front of it? Making
Mm-hmm.
2. What about the one to the right? 3.
Mm-hmm.
The one to the left? 4. Then the one up and down, 5, 6. Do you get the point now? So you can see
Yes.
that each chloride has 6 sodium surrounding it, and each sodium has 6 chloride surrounding it. You have to know how to say that. You have to describe the lattice structure of sodium chloride. Just say that, it contains alternating arrangement of Na plus and Cl minus. That's 1 mark. Now tell that each sodium ion is bonded to 6 chloride ion, and each chloride ion bonded to 6 sodium ion. So can you now see now? Just say number 1. Crystals lattice of sodium chloride contain Na plus and Cl minus arranged in alternating manner. Number 2, each
Mm-hmm.
Cl minus or each ion is bonded to 6 oppositely charged ion. That's the better way of saying it. Each ion, you can just say each ion is bonded to 6 oppositely what? Charged. Do you get the English?
Yeah.
Ions. Good. Can you just say that? That'd be perfect. That's 2 marks. Is that okay? So we are
Yeah.
done with giant metallic, giant ionic. Now giant molecular now. Yeah, go on.
Giant molecular solids or micromolecular solids. Most are insoluble in water. They
Mhm.
exist as giant molecular or covalent solids with strong covalent bonds holding the particles together. Hence, the melting points are usually high. They do
Mhm.
not conduct electricity because of the absence of mobile electrons, exception is graphite.
Thank you. Common
Common
examples.
examples: graphite, diamond, boron, silicon, and most metalloids. And compounds,
Common examples. These are elements. These are not
elements.
compound. Is that okay? Yeah, go on.
Compounds, silicon
Carbide.
carbide, and boron
Boron
nitride.
nitride. It's okay. Yeah. Go on. Graphene.
Graphene consists of one layer of graphite. It is also another allotrope of carbon. Graphene has a giant molecular structure, high melting point, and it is an excellent electrical conductor due to the presence of delocalized electrons.
So graphene is like graphite, but just one layer of graphite. Do you get the point now?
Mhm.
Settled. Now I put some things there. Yeah, can you read? Let's do it together. Yeah, go on.
That's what word is that?
Let's
Based
do it.
on
It's called
based.
SAQ, mean self-assessment questions.
Okay.
SAQ, self-assessment questions. So can you read?
Based on structure and bonding, explain why diamond and silica whereas are hard, whereas graphite is soft.
Yeah. Why is diamond and silicon hard? Where graphite is soft? Why?
Because of their giant
They are both
covalent.
giants. They are both giants. Just say diamond and graphite. They have strong covalent bonds only. But graphite has strong covalent bond along the layers, weak van der Waals forces in between the layers. The van der Waals forces allow the layers to slide over. It's that way they are soft.
Mm-hmm.
Something that has is that okay? So Diamond and silica, they have strong covalent bonds only. Is that okay?
Yes.
Diamond and silica, strong covalent bonds only. Strong covalent bonds only. What about graphite? Weak forces among the layers, so it is soft. Weak forces in between layer, weak forces in between the layers. Is that okay?
Yes.
That is soft. Yeah, go next one.
Diamond is a poor electrical conductor, while graphite conducts electricity.
If they say 1 mark, you just say, oh, diamond does not have the localized electron. Graphite has 1 mark. But if you say 3 marks, what we tell them apart from that point? Tell them that diamond, look at diamond, it has 4 covalent bonds. Remember, each carbon atom has 4 outermost shell electrons. This is diamond in the middle. It's also here, you can continue again. It has 4 covalent bonds. Is that okay? So that means it uses all the 4 electrons in the outer shell to form 4 covalent bonds. Do you agree? What about graphite? Graphite is like this. This is diamond, graphite atom. Graphite atom. How many covalent bonds does it have? How many does it have? Count it for me now.
2, 3, 4, 5, 6.
3. No, consider each dot. How many covalent bonds each dot has? 3. 1, 2, 3. So each dot means carbon atom in graphite. Each of the carbon atom form 3 covalent bonds. The 4th electron now become delocalized around each carbon atom. Should I say that again?
Yes, please.
Diamond, 4 outermost shell electron, 4 covalent bond, therefore no delocalized electron. But graphite, out of the 4 covalent bond, it uses 3 to form 3 covalent bond. Is that okay? So that each atom now has 1 electron not used in bonding. So that electron is delocalized around each carbon atom. Do you get? Making it an excellent electrical conductor. Now let me say some other thing. Let me close this. Now, diamond graphite. I want to say something about them. Diamond. What do you mean by diamond? 4 covalent bonds per atom. 4 covalent bonds per what? Per atom. No delocalized electron. No delocalized electron. Tetrahedral arrangement. Tetrahedral arrangement is tetrahedral arrangement of atoms. Are you following me? Bond angles 19.5. Bond angles 105 degrees. I'll skip that. It is sp3 hybridized. I'll teach you that. I know I skipped it. I didn't teach you. Let me leave it for now. I'll teach you. It's when you have 4 sigma, 4 single bond. This is carbon atom. Under carbon, under carbon, under carbon. Focus on this. That's 4 covalent bonds. So sp3 hybridized. Graphite. Graphite is what? 3 covalent bonds. 3 covalent bonds per atom. So, how many type of bond do we have in graphite? 2. Covalent bond and van der Waals forces. What about in diamond? Only 1 type, covalent bond only. Do you get the point?
Yes.
So, 1 delocalized electron per atom. 1 delocalized electron per what? Per atom. What's the shape of graphite? Is hexagonal planar based on trigonal planar unit. Hexagonal planar, like hexagon. Based on what? Based on trigonal planar unit. I will explain that in a trigonal planar unit. It's like this. You consider the carbon atom and the shape. Trigonal planar, 120 degrees. Trigonal planar, 120. But the whole thing form an hexagon. You agree? Trigonal planar. Trigonal planar. So bond angles 120 degrees. 120 degrees. Bond angles. That is sp2 hybridized. Is that okay? When you now come to fullerene, it's similar to the graphite. Is that okay? One layer of graphite is the same thing. Anything using graphite, using the one layer of what? Of graphite. When you now come to, no, not fullerene, graphene, I mean. You know what they call fullerene now? Do you know fullerene?
No.
Yeah, look at fullerene. This is one example. It's like a spherical ball. So look at the dot here. Look at, if you see my cursor, can you see my cursor? This dot is a carbon atom. Carbon atom. Carbon atom. Carbon atom. Is that okay? So it's like graphite. It has a covalent bond. Look at this carbon here, this dot here. A bond up, a bond this way, a bond down. Do you agree? So each carbon atom has a bond. So fullerene also have the localized electron. Do you get the point now? There is a simple molecular structure. The electron do not flow across the whole length, so it does not conduct. When you have localized, the electron will be able to flow across the whole length of your structure. This one fullerene is separate from the other fullerene. The two fullerene atoms are held together by weak van der Waals forces. Is that okay? So the van der Waals force does not allow the electron to flow. It doesn't allow it to flow. Do you get the point now? So my point here is this. It has delocalized electron, fullerene, please know that, but does not conduct. Why? The electron do not flow outside it. Just like when you say you have a lake and a river. Can we use a river to generate electricity? Yes, we can use a river to generate, but you can't use a lake to generate it. The water does not flow, it just stays in one place. It has water, but it stays in one place, it doesn't flow out. So in the graphite, the electron flows out, so it conducts. In fullerene, though it has the localized electron, it does not flow out. Do you get it now? It does not conduct. It's within this guy. Now, let me tell you what I mean. Look at it. Now, come and see fullerene. I'll draw one for you. Fullerene. Fullerene is like, let's say this fullerene. Under fullerene. Under fullerene. They are connected by van der Waals forces. Electrons don't flow across, but they flow along covalent bonds. So you can look at this fullerene now. Can you see?
Yes.
I'm drawing fullerene for you now. It contains hexagon and pentagon. Each carbon atom here, can you see that's only 3 bonds? 1, 2, 3. But if this is covalent bond, it will have conducted. If this is covalent bond, it will have conducted. But it's not covalent bond. Fullerene. This is fullerene atom. This is fullerene. This is fullerene. This is fullerene. Now pay attention. The formula is C60. 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 What hold them together? What is this? Van der Waals forces. What is this? So electron do not flow along van der Waals, it flow along covalent bond. So electron does not flow across, though it has the localized electron, it does not conduct. Fullerene has the localized electrons or electrical conductor because it is simple molecular. It is simple molecular and electrons do not flow across the whole structure. Do not flow across between two molecules. Now, bond angle in this guy, come and see. Oh, I've closed it. Bond angle in this guy. It contains hexagon and pentagon. Do you think it has only one bond angle or more than one bond angle? Look at it. It contains this. It contains this. And they also contain this. Hexagon and pentagon intertwined together. Is that okay? Hexagon in math, this is a polygon, right? internal. Yeah, 3:30. Wọ́n ti fẹ́ lọ sùn oúnjẹ mi lọ bù sílẹ̀ lọ bù sílẹ̀. Now, are you there now? So bond angle, this bond angle, call it A. Whereby this one call it B. They are different. A is not equal to B. Do you agree?
Yes.
In mass, you can calculate that. Am I right?
Mm-hmm.
Sum of angle in a polygon is what? Equals to n minus 2 into 180. Am I right? You can find the bond angle on each of them. Sum of angle in a polygon, the sum of angles in a polygon. That is a 2n minus 4 into 90, or n minus 2 into what? 180. So for the hexagon guy, for the pentagon guy, what are the bond angles in that guy inside the pentagon? What would the answer be? Pentagon n is 5. 5 minus 2 into 180
Times
into 180. That's 540. Then each angle will now be what? Divided by 5. Each angle,
108.
thank you. Each angle is now what? 180 degrees. Now do the exercise one for hexagon. For 1 year, they asked that, is there only one type of bond angle in fullerene? I said no. There are two types of bond angle there. It has a bond angle for hexagon different from that of pentagon. Is that okay? For hexagon, what does that be? Hexagon. It should be what? 6 minus 2 into 180. That's 720. 720 over
120.
6. Is 120 differs. So it has more than one bond angle. But all the carbon atoms are trigonal planar. So they are also sp2 hybridized. So they are sp2 hybridized, like graphite, sp2. When you form 3 covalent bond, you are sp2. When you form 4, you are sp3. Is that okay? That's fine. Now let me see. We are not done with this topic. Now, ionic solid are brittle. Why are metals are malleable? Can you explain it to me?
Ionic
Ionic
solids.
solid. When you exert a pressure on them, come and see. Exert a pressure on this. Where's ionic solid? You can see ionic solid as, I hope you can see it as this. Let me see. It's correct what I drew here, but you can also see it like this. Ionic solid can be seen like this. Na plus, Cl minus, Na plus, Cl minus, Cl minus, Na plus. Am I right? Cl minus, Na plus, Na plus, Cl minus. This is ionic solid. Do you agree? When you exert the pressure on them, two similarly charged ions are brought close together. You repel each other and the whole thing shatters apart. When you apply a pressure on an ionic solid, why they are brittle is that when you apply a force on them, the force can bring two similarly charged particles together. This will repel each other and the whole thing shatters apart. Is that okay? Do you get the point now? They are brittle. Now, in graphite, ammonia is what is sp2. In diamond is sp3. Let me see it. What's the geometry orientation of carbon atoms in each allotrope? In graphite is what? Trigonal planar. In diamond, tetrahedral. Trigonal planar. Diamond tetrahedral. Tetrahedral. This is it. Where is it now? That's it. Boron nitride. All these guys are giant molecular structure. Boron nitride. Now, look at boron nitride. It's a giant molecular structure, like almost like graphite, right? What group is boron? Boron does not, is a group 3 element. I use all the 3. So that means each of nitrogen has a lone pair. Do you agree? Lone pair. Lone pair. Lone pair. Do you agree? You do something like this one. You say which of the atom has lone pair. Nitrogen is a group 5 element. Shares 3 electrons. You have 2 electrons. You have a lone pair left. But boron is group 5. It doesn't have any electron left. I'm in group 3. He shares the 3 and nothing left for him again. Now, simple molecular structure. Let me see. Are we almost done? Yeah. Yeah, easy. We're almost done. Let's finish. You know, we know we are done with this topic. Please. Yeah, can you start? 3B. Can you start reading?
Simple molecular structures. The atoms within the molecules are held together by strong covalent bonds, while the molecules themselves are held by weak intermolecular forces. For example, van der Waals forces. Common examples include elements sulfur, phosphorus, and iodine.
What does that mean? Can you tell me what that means? Please stop there. Now, simple molecular. Simple molecular. You are saying that sulfur and sulfur is S8. Strong covalent bond between them. Do you agree? Draw another one. That's sulfur molecule S8. Draw another sulfur molecule S, 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 S. Now, show me the intermolecular force between them. Look at it. This guy. Weak inter. Can you see now? What is that? Weak intermolecular forces. Am I right?
Yes.
So now, can you write an equation for me when sulfur melts? So this guy are what? Weak ID forces. Now, when sulfur melts, look at sulfur. It was S8 solid. When you hit it, you only break the bond. You break the ID force. It become what? It's still S8 liquid. You didn't break the covalent bond. Again, S8 what? S8 gas. Do you agree? So when sulfur undergo a change of state, what type of bond are you breaking? ID forces or van der Waals forces? Do you get the point? So S8. So now P4. What's the valence of sulfur here, class? 2. Am I right? Sulfur is 2.
Yes.
That means sulfur has 2 lone pairs on it. We didn't just show it. Am I right? They are there. 2 lone pairs. Now phosphorus is valence 3 and it's P4. This is P4. Please pay attention. P. How many bonds do each of them have now? 2 bond. One now stay on top here. You now join to this. P. Join to this. Join to. Can you see now? Such that each of the phosphorus atom now has how many covalent bond? 3 covalent bond. Is that okay? Do you get the point now? This is P4. This is under P4 now. Do under P4. P. Sometimes they draw like this. You see the same thing. P. This, the first one is better. So between P4 and P4, weak ID forces. When P4 undergo a change of state, you are not breaking the covalent bond. You are only breaking the ID force between the molecules. Is that okay? So which is very, very weak. So what do we have here now again? ID force. Can you see now? ID forces. Can you see now? Now hold them together. Is that okay? Now, the more the number of electrons in them, the stronger the ID forces. So S8. How many electrons do we have in S8? Sulfur is 16 times 8. 128 electrons. P4, 51 is 15. 15 times 4, 60 electrons. Cl2, when is 17 times 2, 34 electrons. Argon is number 18 and it's a single atom, 18 electrons. So when you consider this guy, melting point decreases this way. Do you agree to that? Number of electrons decreases. Strength of ID forces decreases. Melting point or boiling point decrease. Is that okay? Are you sure you understand this? If they
Yes,
are smooth molecular structure, the more electron they have, the stronger the ID forces, the stronger they are the melting point. Let me see this as state of matter. I don't want to disappear. I was saying it alongside with you. Please, when I'm not telling you we round up, let's just finish this topic. I'm not going to this topic when next time I meet you. We're going to topic 5. Can you see now? Now, each time we should be finishing the topic now because the one that's taking our time, we finish it. Topic 6 is enthalpy change. We should finish when we meet it. 7 equilibrium, we should finish also. I have notes on them. 8 stages of we should finish when we meet them. So each time we meet now, we should finish a topic till we finish. So it won't take us time point. We'll finish those syllabus. Is that okay? Those
Yes.
one at the beginning are the one that takes enough time. Kingston. The state of matter. State of matter. Class notes. Steve. Let me see this one, even this one. 1 minute, please. Yeah, let's go. Let's finish up. Let's finish up this. I've saved this. Now, so we have seen those things that they asked us there. So so yeah. So elements, sulfur, phosphorus, and iodine. Gaseous molecular element like H2N2O2, Cl2, F2O3 exist as single molecular substances with weak van der Waals force between them. Compound. Most covalent substances which are gases, liquid, or solid are simple molecular substances with weak van der Waals force between them, hence between their molecules. Example, gaseous and liquid hydrocarbon, CO2, Cl4, all those things, they are simple covalent substances. Is that okay? Yeah, now what can you say about them? Can you start reading from here? These guys.
They do not usually dissolve in water.
Mhm,
They exist as gases, volatile liquids, or
mhm.
volatile solids. They do not contain they do not contain molecules, ions, or molecule electrons, and are therefore poor electrical conductors.
Okay.
Most of
Most of
them,
them dissolve in non-polar solvent. They have low melting and boiling point because the weak forces are between their molecules, and they have little amount of energy to heat them apart. Fullerenes or buckyball or buckyballs are fullerene and that group of carbon. These are spherical structure which are based on hexagonal and pentagonal units. Carbon atom are sp2 hybridized, and each carbon atom has a delocalized electron around it, but these localized electrons are intramolecular and cannot function as a conducting electron cloud. They are simple molecular with weak ID force between their molecules due to the constraint and due to the constituent hexagonal and pentagonal unit. Two different bonds angle here. Can you do you understand what I'm saying now?
mm,
Due to their constraint hexagonal and pentagonal units, two different bond angles exist around each carbon atom, though all carbon atoms have trigonal planar geometry. There are two bond angles in what? In fullerene. Is that okay? Because it consists
yeah.
of hexagon and pentagon. Adding bonded solid. Yeah. Ice, proteins, DNA, sugar, glucose, sucrose. Bonding is covalent, while the intermolecular forces are what? Are hydrogen bonding. So they have covalent bonding and they have intermolecular hydrogen bonding. Is that okay?
Mm.
SAQ. Let's see what happens when a given mass of water freezing to ice. Water and ice, which one is heavier? Which one is
Water,
denser? Ice float on water. Why do ice float on water?
water is denser.
Uh, Based on structure, tell me why now. Ice,
Oh,
let me show you let me look at what it looks like. This is water molecule in ice. There's extensive hydrogen bonding in ice. This ice for you. Hydrogen bonding, hydrogen bonding. There's no space between them. Water. This is water and hydrogen bonding. Can you see now? Hydrogen bonding. Water. Hydrogen bonding, hydrogen bonding. Now, what is this now? Now, pay attention. Now, what is this? Empty space, empty space, empty space. Can you see now? So in
yes.
water molecule, there is extensive hydrogen bonding. And water molecules in ice, in ice, there is extensive hydrogen bonding. Water molecules in ice are arranged so that there are spaces between the water molecules. And at the end of the day, it occupies larger space and therefore lower volume. Do you get lower density? Do you get the point now?
Yes.
Ice, I'm telling you why ice float on water now. So that it has to ice floats
Mm-hmm.
on water. Why? Ice has extensive network of hydrogen bond. Had extensive network of what? Of hydrogen bonding. Such that water molecules are not closely packed, such that H2O molecules in H2O molecules in ice are not closely packed, are not closely what? Packed. We normally say ice has an open ice. No, let me write for me. Closely what? Closely packed. Full stop. Ice has an open is open in inverted comma, open inverted comma, open what? Open molecular structure with spaces in between the water molecule, with spaces, with empty spaces between the water molecules, with empty spaces between what molecules. What does that mean? Hence, greater volume and lower density. Greater what? Volume and what? Lower what? Do you know what I'm saying now? Ice
Yes,
has extensive network of hydrogen bonding such that water molecules in ice are not closely packed. Ice has an open molecular structure with empty spaces between water molecules. What does that mean? It occupies a larger volume and hence it has a lower density compared to water. Do you get the point now? So
yes,
when
I
water
do.
freezes, what happens to water when it freezes? Will it increase in size or decrease in size?
Decrease.
No, it will increase in size. Look at it, water. Pay attention now. This is water. And then it
Oh,
turns to
yes,
ice.
decreases in size.
Because it has a larger volume, it will increase in size.
Mm-hmm.
Go and try it at home. Fill up your water to the brim, put it in the freezer. But then don't try it. You'll have seen it will have gone above the cover, above the water. Or you put it in the fridge, mark it, you can mark it, go and mark it. And then don't try it, it become bigger in size. It just that means it increases in volume, therefore it has lower density. Therefore, when water is freezing, where will it stop? Where will it start freezing from? From the top of the bottom. When water is freezing,
The top.
will it,
From the
from the
top.
top, thank you, from the top. Because ice can never be below water, it's only on the top. Only be on top. Do you get the point? Now, these guys now,
Yeah.
and I explain them to you now. I gave you by 5 substance. I will do only 2 of them for you. Look at number 1. It has melting point in the negative, boiling point above room temperature. This is a solid or liquid or gas under room condition. Room temperature is 25. This guy will not boil until 78. So, and it has turned to liquid from minus 114. So this guy is a solid or liquid or gas under room condition. It has turned to liquid at minus 14. It should not boil until 78. So under room condition, which is 25, is it a liquid or solid or gas?
Solid.
This guy has melted since minus 114.
It should be a liquid.
Thank you. It's a liquid. It has melted. Now, let me tell you how to do it. Now, look at it one by one. Take one by one. A. It has melted before room temperature. It has not yet boiled, so it's a liquid. Look at B. It does not melt. It melts after room temperature, so it's a solid.
It's a solid, yeah.
Look at C. It melts and boils before room temperature, so it's a gas. It melts. It also boils before you even reach room temperature. Do you agree? It's a gas.
Yes, yes, sir.
Are you sure there? Are you sure about that? Let's go on. This guy does not melt until 1000 is solid. It
Which
melts
one? Number
above room
4?
temperature. It's solid. That D.
D. Okay.
It's a solid, right? What about
Yeah.
E? E is also a solid. F
Melts
is also a
above.
solid. G is a solid. H is a solid. J is a solid. They are all solid. Do you agree to that?
Yes.
Who are those that are liquid? Somebody that melts for 25 degrees Celsius and boil after 25. If it melts and boils before 25 degrees Celsius was reached, it's a gas. Let's do that again. If it melts and boils before 25 degrees Celsius was reached, that means a gas.
Yeah.
Do you get the point now? Good.
Yes.
So now, so you can see this guy now. Turn the fan for So that's it. So hey, look at A. In solid state does not conduct. In liquid state does not conduct. In aqueous state does not conduct. So it's not ionic. It's a simple molecular structure. Do you agree? So it's a liquid.
Yes.
Agree? So look at A. Look at it. Can you read A?
A
Look at
is
it.
a simple molecular liquid soluble in water but does not ionize in aqueous solution and hence a poor electroconductor. A could be an organic liquid which is soluble in water, for example, lower molecular weight alcohols, aldehyde, ketone, ester, carboxylic acid, amine, etc.
Do you get the point now? A does not conduct. Look at them. Dissolving water is a aqueous. It doesn't just conduct. It's dissolving water, but it doesn't conduct in water. Is that okay? So it's a simple covalent structure. Do you agree? Look at B. What can you say about B?
Okay.
It's a solid. It conducts in solid state and in liquid state. B is a metal. Do you agree?
Yes.
Something that conducts in solid state is a metal. Ionic compound don't conduct in. They only conduct in aqueous state or molten state. Do you agree?
So C
So
is
this guy conducts in the
ionic.
solid state. So it's a metal. Do you agree? It's a metal.
Yes.
Yeah, come and read it. B. Can you read B?
A is a metal since it's a good conductor in solid state. B is insoluble in water, hence aqueous solution does not exist. A could be any D block metal, e.g.
Or it could be. No, I don't mean A. I made a mistake.
B
It's
D
cool.
block.
D block metals are those transition metals. Is that okay? E.g. scandium that do not dissolve in water. It can't be sodium. You know why? Sodium reacts with water and become a aqueous solution. Do you agree? This one does not dissolve in water. Is that okay? Look at C. C is a gas. Am I right? Does C conduct in solid state?
It's poor, no?
It doesn't conduct. What about in liquid state? No. But in
No.
aqueous state, it conducts. So what
Mhm.
could C be? Come and see what I wrote here. Look at it. Can you read it?
C is a simple molecular gas with weak IMFs. C
You know
ionizes
what
when
does IMF mean?
I I don't know.
Intermolecular forces.
Oh, okay.
Intermolecular forces. Which can be what? IDID, PDPD, or hydrogen bond. These are is that okay? That would be IMF. Is that okay? Yeah, go on.
C ionizes when dissolved in water or reacts with it to form an ionic equation. C could be hydrogen chloride, bromide, iodide, sulfur trioxide, nitrogen dioxide.
Come and see. It says C on its own does not conduct. Then what I conduct? When you dissolve hydrogen chloride gas, is it covalent to ionic? Is what? Covalent. When you add water to it and it become ionic. But it's not ionic. Do you agree to that? It's ionic. Because this guy is actually what? H plus aqueous and what? Cl minus aqueous. Hydrogen chloride on its own, it does not conduct. But in water, it become ionic and begin to conduct. You need to get that right.
Okay.
All acid are covalent substances. Pure acid don't conduct electricity. But when dissolved in water, they become ionic and they begin to conduct. Should I say that again? Pure acids are covalent substances. When dissolved in water, they do not conduct electricity. I mean, on their own, they do not conduct electricity. When dissolved in water, they become ionic and begin to conduct. Do you get the point now?
Yes.
Are you sure you understand that?
Yes, sir.
I'm saying that, look at it. This guy, H2SO4 liquid, is covalent. Contain molecules. So poor electrical conductor. Can you see what I wrote? But this guy, H2SO4AQ, it's not covalent to. It's not what? It's ionic. What does it contain? Contain ions. Contain what? Ions. And therefore, good what? Electrical what? Are you sure you understand this?
Yes, sir.
H2O, H2SO4 liquid is pure sulfuric acid. It's a covalent compound. There is no metal there. Now all of them are non-metal. HSO, they are all non-metal. When non-metal, they form covalent bond. They are not non, but in water, it become ionic and begin to conduct. Is that okay?
Yes.
I will stop here. I want to go over the mini example there. I've put the explanation there. Is that okay? So please go
Yes,
over
sir.
there.